Good morning. Thank you for attending my talk. I would like to talk about our SmrtFridge system, which is our attempt to create, which is our first version of an internet-connected fridge. We actually created a prototype of this in our university lab. My name is Amit Sharma. I'm a PhD candidate in Singapore Management University, and this work is a joint collaboration with Professor Mishra, my supervisor, Venki Subramanian, and Professor Yong from Seoul National University. So, over a period of time now, a regular household fridge might start with something like this. So many items stacked horizontally or vertically behind each other. And the SmrtFridge system is our attempt to create two key features for this situation. First, we want to assign a label to all the items inside the fridge. For example, this is a ketchup, this is an orange juice, and this is soy milk, and so on. Secondly, we want to estimate the quantity of all the items. How much content is remaining inside the fridge for that particular item. Now, why should we care about this? What can we do with these features? So there are a set of potential applications which we can develop on top of this. For example, the personalized alerts. Imagine you are passing by a supermarket and your fridge reminds you that, hey, your orange is about to finish. Why don't you buy one? Another type of alert could be like, hey, I think this milk carton you put in like 2 weeks ago, you're not consuming it. It might have expired, so why don't you check it? So in a way, it helps you track like what food items are kept inside and your uses over a period of time. And apart from these, there are other applications like automatic shopping list creations and smart recipe suggestions and so on. Now we interact with the fridge on a daily basis, probably multiple times a day. So in order for these features to be useful, we believe there are two key usability requirements. This system should be automatic and unobtrusive. I, as a user, do not want to do any manual effort for the system to recognize this. I just want to do my natural gestures, and still the fridge should be able to detect both these points. Now, the previous alerts, focusing on the SmrtFridge, actually can be broadly classified into three categories. First one is the RFID or barcode-based systems. So what they do is they install a sort of a scanner, like a RFID scanner inside the fridge, and then they tag the items with an RFID tag. So every time you are interacting with the fridge, the scanner will find out what items you are interacting with. And similarly, the barcode scanners, they scan the barcode when you are interacting with the items. One key issue with this approach is it will shortly become non-scalable. So imagine this. You have a set of items inside and they are about to finish, so you want to replace them with new items. Now you have to take out those RFID tags, remove them from the old items, put them onto the new item and manually map. Okay, this RFID tag now, map into orange juice now. So shortly it will become a non-scalable system. The next category for this kind of work is mobile app based. So in this system you have your mobile app, and every time you are bringing in a new item, what you do is you manually scan that item using your smartphone, for example, a camera-based barcode scanner, and then your mobile phone actually maintains the inventory for what is inside the fridge. Clearly, this kind of systems are actually, they require you to do manual work, and this is clearly oppressive. Last category, it follows the fridge-based cameras. So there have been some commercial attempts as well following this line of work. What they do is they will install a couple of cameras inside the fridge, which are actually looking inside the fridge, and at some point of time, for example, when you're closing the door, they take a snapshot of the fridge, and then they try to identify what are these items. One key problem with this approach is, can you see the items behind these items in the front? So there is a heavy occlusion. And on top of these issues, there is one more feature that is missing. None of the categories actually provide any solutions for estimating the remaining content. To this point, let me introduce the SmrtFridge system. It follows our design philosophy of a user interaction-driven system, which means that as and when the user interacts with the fridge, the system will capture that interaction, and for each such interaction, it will identify what is the item inside. For example, consider this interaction. For this particular interaction, the SmrtFridge will say, well, it's a guava juice and it's only 20% remaining. So that's how the system works. Now, let's say we have captured the user interaction. Now, what is the next question? The next question is, how do I identify the item? How do I know which item is it? From this user interaction, can we just take the full frame and try to like find the item inside it because the frame has the item, right? So can we like identify that? We have tried that. We have tried to classify the full frame, and what we got is very poor precision and recall values. But since the frame has the item, what is going on? Like what is the challenge here? Why is it not able to recognize it? Let's look at that in detail. So this is one frame from the interaction, and now this contains the item that we're looking for, but there is a problem. There is so much undesirable content. For example, there are items kept in the fridge door, then there is a user, and there is possibility of the background behind the user. So all these things are actually contributing to a low precision recall score, and we need a mechanism where we can pinpoint to the item inside the frame. So that is the first challenge, that how do we accurately identify the full items from a given set of images. Next challenge is from the quantity estimation. So there are containers like in various shapes and sizes, and then some containers are transparent, some containers are opaque. So the challenge is like how do we estimate the quantity for all of the containers. Specifically for transparent and opaque containers, we can see through the transparent containers, but what about the opaque containers? How do we know how much content is left inside? That brings me to the second challenge, which is how do we estimate quantity inside the container. How does the SmrtFridge system handle these challenges? Let me introduce the key idea. For the item identification part, the key idea is that we're using a combination of infrared camera plus the RGB camera. So this is how the images look like from both the cameras. The RGB image is basically, it doesn't need much explanation. It captures what we see from the eyes. But on the other hand, the IR image, it basically captures the thermal profile of the view, which means that depending on the relative temperature of the objects in the view, it will give a different color. The hotter objects, for example, the human body here, will be like on the brighter side, they look brighter, and the colder objects will look darker. So the cold item here is the most darkest one. This is the key property that we're using to segment the item from full frames. At a high level, this is how the pipeline looks like. And let's say the user did an interaction with the fridge, we capture that interaction as a set of RGB plus thermal images. So it's an interaction, so there will be a set of RGB plus thermal images. We take each image and we do item segmentation on that. This item segmentation is completely led by the thermal camera using the property that I just described. Once we have the segmented item, what we do is we send it to a DNS classifier which is sitting in the cloud, and it gives us the label for this. I'll describe this pipeline in more detail in the coming slides. I would like to point out one thing. So this classifier, now we have trained it on the items that we have experimented with, but we do not see this as a main contribution of the paper because in our reason we believe that this classifier could be a third-party classifier sitting on the cloud, which could be used for all the homes and all the setups of SmrtFridges. Next, moving to the quantity estimation, the key idea behind the quantity estimation. So the problem was how do we look through the containers and how do we estimate the quantity. Again, we are using the thermal camera for this. So from a set of the thermal images, what we do is how do we extract the quantity. So this is the property we use. This is an infrared image for two containers that we just took out from the fridge. Let's call it T equal to 0. Now one of the containers is actually full and the other container is partially filled. But right now we cannot differentiate which one is full, which one is partially filled. So if we keep these containers outside for n number of seconds, this is what happens. The container on the right side, which is actually partially filled, you see two different thermal clusters within that container. The upper part, which is the empty one, has suddenly become a little bit more bright than the part that is filled. Why is it happening? Because the upper part, which is empty, that contains the air, and the lower part is basically the liquid. And there is one property which each substance has, we call it specific heat property. That property basically governs how rapidly a particular substance will gain heat. And this property value for the air is actually pretty low compared to the, for example, water, which means that air will actually gain heat faster than water. And that is the key principle that we are using to estimate the quantity. Now let's look at the high-level steps of how does this happen. So from a user interaction, we have a set of thermal images spanning across the whole interaction. what we do for each of these images, we actually do the item segmentation again using this property of the thermal camera, and from this we send this extracted items to the quantity estimator, which gives us what is the remaining content inside it. And this quantity is actually expressed as a percentage of the whole container. So it's like 30% full, 40% full, and so on. Now let me move to the pipelines in detail. First, the item identification part. So the input for this is a set of IR images plus the RGB video that capturing the whole interaction, and the output is actually the label. So let's say this is the interaction capture, one of the images. So what the first step we do is the segmentation part. We first find in the thermal image that's where is the location of the cold item. Using a pixel-based thresholding, we can find where is the location of the cold item inside the thermal image. And now this gives us the location, but we cannot classify this because this is just a black and white image, and clearly the classifier cannot identify what is it. So the next step is how do we find the RGB image corresponding to that. Now here we are using a fact that we have installed the RGB and thermal cameras such that their relative positions are fixed. So utilizing that, we have done a sort of a mapping from the thermal coordinates to the RGB coordinates. So when we know the location of the item in the thermal image, we map it to the corresponding coordinates to the RGB image. That gives us the actual item image. And because the interaction is a video, so there are multiple frames, and we extract the item from each frame. After that, we will have a set of extracted items. We send all of these extracted items to the cloud for identification, and each image will give us a label. Then we run a majority voting on the labels, and we say like what is the most probable label from this interaction. Now this pipeline clearly depends on the thermal camera. But what will happen if the thermal camera doesn't work? For example, in a situation when the item is not cold, it's at the room temperature. In that case, thermal camera will not be able to differentiate between the cold item and the ambient objects. For that case, we have a backup pipeline, which we call the visual only pipeline. Because the interaction is a video, we are using the motion inside the video in subsequent frames to extract the item, and then those extracted items will be sent to the DNN for classification. The quantity estimation pipeline, again, it takes a set of IR images for the interaction and gives us the quantity. This is how it looks like. So let's say there was an interaction which resulted into a set of thermal images. Now, since the quantity is a fraction of the container capacity, that is 30% or 40%, we have to discard certain images which are partially captured. It's a gesture, so some images might be partially captured and we have to ignore those images. So that's the first step. After that, we do a cold item segmentation. This is basically a pixel-based thresholding. We put a threshold and select all the pixels below that particular threshold. This gives us the cold item. Now the next task is how do we identify the quantity. From there, we actually run a clustering on that. And the hypothesis is that all the points that belong to the filled part of the container will become one. Will go into one cluster, and all the pixels corresponding to the empty part of the container, because there is a relative difference between the temperature, so they will go into another cluster. And that, having the cluster sizes, if you just divide the empty portion to the full container capacity, that gives us the relative quantity estimation. Now there are quite a few pre-processing steps that I have omitted here for that are mentioned in the paper. For example, we have done something to tackle the occlusion which is caused by the hand. So the user is holding the container, so the hand will occlude certain parts of the container. So we have done some interpolation and a few other pre-processing steps to tackle these kind of issues. Now, having spoken about both the pipelines, let me now talk about the prototype that we created in our lab. We actually used a commodity fridge, and on the right side there is this rectangle which shows this red box actually that shows the location of our camera. All the cameras, it's installed within the fridge, pointing outside. And the blue, if you see the blue light there, that's the thermal camera, and just below that is the RGB camera. The sensors we have used is Raspberry Pi with the Pi cam, and there's a thermal camera. It's a FLIR laptop module which is assembled by the Interforge. And then there's a door switch with the magnetic switch. The total cost for all these sensors, excluding the fridge of course, is around $300. And a typical fridge actually usually costs $1,000, where you get the full system. Now let me move to the performance analysis for both the pipelines. For the item identification, we recruited like 12 users and we covered 19 food items. These are the items that we probably that we mostly use in our day-to-day life. For example, the juices, the soda, and the milk bottles, and so on. And we also added some fruits and vegetables to cover the wide range of food. All the participants actually there were no specific instructions in like what order you have to pick the items and what kind of gestures you have to make. They were free to choose which item they want to pick, whatever order they want to pick it, and whatever way they want to pick it. From this data, actually we analyzed this data, and I want to talk about two classes of the accuracy. First thing is the item segmentation accuracy. So from the collected data, we run out both the pipelines and then the extracted items. And the accuracy for that, the evaluation metric for this item segmentation is IoT score. IoT score is basically this. So given a frame, there is an item in the frame. Let's say there is you draw a bounding box for the actual item location, and then there is a predicted bounding box. IoT score basically tells you how much they are overlapping. The more overlap, the better the algorithm. I'm going to show a graph here, which x-axis here shows the IoT threshold, and the y-axis shows the corresponding percentage of the images which are above that IoT score. So we have extracted the item from all the data we collected, and for each IoT score, we are saying like out of those extracted items, how many are above this IoT score. So the green line here is actually when we merge both the pipelines. So you get an input from the MV pipeline, which is the motion vector only, which just uses the RGB images, and IR driven is basically the thermal gamma driven pipeline. And the third one, which is shown here by the green line, is actually when we merge the output. So whichever pipeline gives us the higher confidence, we take that input from the pipeline, and that's how we merge it. We found that the merged pipelines actually works best. For example, let's say IoT threshold of 0.6. We found that the merged pipeline, almost 85% of the images, of the extracted images, had an IoT score of at least 0.6. Then we also checked the accuracy of the classification, which means that the extracted item is sent to the DIN and then we get the label back. So what is the accuracy for that? And I'm going to go the primitive recall as a metric for this. And what we found is, let me talk about the baseline first. The baseline is when we use the full frame and send it for classification, and we get the item label. That's the baseline. And again, similar to the previous case, we found that when you merge MV and IR, we get the maximum precision recall of 8484. And both the other pipelines are slightly behind this merged pipeline. So merged pipeline kind of captures the best of both the pipelines. Moving to the quantity estimation performance now. For this, we collected data from like 7 different users. And we chose 3 different liquids: milk, solid, milk, water, and juice. And then we experimented with 3 quantities. So we chose 30%, 60%, and full containers. We wanted to see like can we differentiate between all these quantities across all different users. And so this was a sort of a semi-controlled study, which means that all the participants were asked to take out items, whatever items they want to take out, but they were asked to like put those items outside the fridge for about 20 seconds and then put it back. So I'm going to show a box plot here, and the x-axis represents the actual quantity, and the y-axis is like the estimated quantity for this. And the idea here is that for each liquid, can we separate the estimated quantity from is it 30% or 60% or full? For water, we found that we could actually draw a horizontal line between all these 3 categories, and we were actually able to separate this. Milk was probably the best among all the 3 liquids, and then the juice was the most noisiest one, especially at 30%. And we found that there is actually a correlation between the specific heat property of juice and the results being noisy here, because among the 3 liquids, the juice is actually closer to the specific heat value of juice is actually closer to air, which means among these all three liquids, juice has a tendency to gain heat faster than the other two liquids. So we see a noise in the quantity estimation here. Then we also actually created a classification model on top of this. So what we did is actually we took all the three quantities and we created a plus minus delta Q kind of bar. For example, for 60%, if the estimated quantity falls within plus minus delta Q of this 60%, we classify this as a. So the performance for that is actually 75 precision and 71 recall. This is more of a sensitivity study. For example, when you are inserting something into the fridge, you may not hold the container straight. You may be putting this container like this at an inclination. So we wanted to know like what will happen in that case. So we took one liquid and three different quantities, and we saw that except at the angles 0 degree and 180 degree, where the errors were high, we were actually within 120%. But why is that? What is happening at 0 and 180 degree is so this called out. The green part is where the content is, and the red one is where the empty part is. So if you move this container, there is a high probability that the liquid will touch the surfaces, and that's what's disturbing the thermal camera. Now, in the current implementation, we have a couple of items that are slightly out of the scope for this current implementation. And first one is the fine grain sensing. We are doing a post grain sensing. And this is primarily because of the resolution of the camera we are using. We believe that if you use a higher resolution camera, then we can use better performance. Second thing is the identical item detection. Current implementation cannot differentiate between two instances of the same item. And lastly, the privacy concerns. Because the camera-based systems have their own privacy concerns. Then we believe that we could use a narrow FOV cameras or face blur kind of systems to tackle this. All the results that I've spoken so far actually are in context of the fridge, but are there any broader applications? I would like to do two applications for that. So item identification part, we believe that there is an opportunity to do automatic product identification at a warehouse. So as and when the products are being unloaded at the loading bay, so the thermal camera can detect the items and you can automatically update the inventory of the warehouse. For the quantity estimation, there is an opportunity to, for example, in case of the refrigerator medicines, if the medicines are spoiled, then there could be a difference in the density. And if you combine the weight sensor and the thermal camera, so you want to wait for the medicine and then you estimate the quantity using the high resolution thermal camera. If they don't match, then probably there is a problem. Lastly, for the takeaway points, so we presented the SmrtFridge system, which offers two key features: the item identification and the quantity estimation. And the key idea is the use of basically the IR camera and the RGB camera, which helped us extract the items and estimate the quantities even in the opaque containers. And lastly, the performance. We found that for 86% of the extracted images, we could achieve an IOU score of at least 0.6. And for the classification, we got 84% precision for item identification. And for the quantity estimation, we could 75% of the time we could differentiate between different quantities of arguments. So that's the end of my talk. Thank you.
Thank you.